break, Commodore, he made a couple of comments about this Region 2 test. He's going to talk a little bit more about that later today, but basically when we do the depletion to get an immobile oil saturation through condensation, if you go too high, then there's a possibility that you could get some liquid flowing out during this third flow of the equilibrium gas. So basically we limit the saturation, equilibrium saturation somewhere between 0.1 and 0.2 to get that 1 point. In addition to that, he mentioned that we often ask the lab to run multi-rate flow tests at as high of gas velocity they can flow with the same equilibrium gases in 3, and that's to get an estimate of the two-phase Forsheimer beta term, this equation in the Forsheimer, or the constant in the rock property in the Forsheimer equation. But when there's two phases, that is no longer a rock property; it's a rock saturation property. So that's a couple of notes he made. We'll return to this later. Okay, so basically in this, when we get the mobility here, we basically calculate that mobility, and instead of the mobility for dry gas would continue up like this, and then start coming down here linearly. We lose this area here, and that area under the curve basically is the area used to multiply by the constant. Okay, let's see here. Okay. This we looked at yesterday. This is the KRG versus KGKO for different. Basically, this pore size distribution reflects the same as the exponent on the saturation exponent on the KRG and KRO relations. So you see this change in the fundamental relationship here as a function for different rock types. Let's see here. That's and this was the calculation we talked about this morning. For black oil and compositional. So I think this is what we did calculations of yesterday. We basically create different estimates of well stream compositions from the initial well stream to depleted gases. And for each of those well streams, we do a CCE to get the KRG, KRO figure shown on the curve above. And then we look at the pressures in the region 1, typically around between 1,000 and 2,000 psi, and that gives us the range of expected KGKO throughout the life of the well. So for rich gas, here it's going from about 1 to about 20, and for a lean gas, it's going from about 8 to maybe 50. Okay, so that's that. Before we go into this, so the volumetric rate equation for a gas condensate well can be expressed in terms of the two-phase pseudo-pressure integral to account for the condensate blockage, where the KRG is inside the pressure integral and therefore has to be evaluated. Can be modeled with the 3 regions around the well. Closest to the well, where you have both oil and gas phases flowing, will dictate the majority of the productivity loss, condensate blockage. Now, the flowing composition is constant in region 1. And actually, the example given in this E note here, we'll look at it, allows you to extract from the model what's necessary to get the flowing composition or the flowing GOR in black oil terms. So we'll show you how that's done. The single phase gas entering from region 2 into region 1 has the same composition as the producing well bore mixture of the well stream. We derived that KGKO relationship. The pseudopressure integral can be used to model condensate blockage in coarse grid reservoir simulation models, or it can be combined with just general material balance models to provide a simple model for condensate well performance. Now, this point 4 has a major problem in really doing that. I know Bob Mott, he published a paper, but the problem is for this point 4 here. I'm just going to, I think, copy it out and snip it to make it. Try to at least. Yeah. And I want to comment on this because I don't know if anybody uses MVAL, and I don't really know the method that it might use in material balance of gas condensates. Maybe that's a question I could ask the participants. Has anyone used MVAL for gas condensate reservoirs?
I have used
it. Working here, or no. Okay. So I just want to make some comments about what you have to be careful about. So there's two options, and I'd say two valid options. Two valid options. Well, it's really one, because if you use the CVD test, you so the material balance, we've already discussed that, I think, on Tuesday, of gas condensate. Can use dry gas, material balance equations, where the CVD two-phase Z factor is used for average reservoir pressures less than the dew point. So that's okay, and that should work. Even if you have aquifer, any of those dry gas. So that's where A and B, the production that's used, the cumulative production, is a wet gas cumulative production, which is the GPD plus this term here. Now, I don't know how something like MVAL handles this, but I assume it can handle both of these things correctly.
Yeah, it depends like how sophisticated you want to do.
I think there is a volumetric conversion for equivalent volume for condensate to gas volume, and also for water volume.
Like fictitious, you convert it into fictitious gas.
Yeah, I'm just assuming that the problem here is that this, basically this is GPD plus, it's kind of like delta GPD times the producing CGR, right? And this is changing in time. So this is time and time. So the question is how does where's that coming from in imbal?
And then COG is also a function of time.
Yeah, but less so than the RP. Okay, so you've got this is an issue, and then you've got COG, which is a weak function of time, or at least a function of time. So how does it deal with this as well? Okay, so you have to answer these two questions by doing example calculations for a simple case. Now, ideally, if I were going to try to do something in this, I would ask to read in from the CVD test the two-phase Z factors, the cumulative, you need, okay. So one possibility in doing this is that if you say that RP at a given average pressure is approximated by the solution RS, where you take that being equal to the average reservoir pressure, okay? That's an approximation that's, let's say, reasonable. This should be reasonable for cum oil or cum condensate estimate, okay? In reality, we know that this is actually less than this, okay? And it's less than that by anywhere from maybe 2 to maybe, I don't know how much it might be, 2 to 8%. Let's say 5% on average, and it varies some. But it's not a big error, but it's an error. So let's say that your cum oil recovery factor is 30%, and this is off, and you're using this assumption, then it's not 30%, it should be maybe 28%. Okay, so I mean, it's not. Yeah. So you need to check whether this is the assumption being made. Okay, probably is. I mean, is what I would guess. So you read in the solution oil gas ratio curve, and you make this assumption. That would be reasonable. But imbal combines the material balance equation with the rate equation, and here's where the problem is going to come. So in a perfect world, imbal used the 3-region model of the Fay-Long-Whitson 3-region model, pseudopressure. So that's material balance. So for the gas rate equation, you should use this QG, what we've been talking about, C, and this integral. Okay, and then that should be this 3-region model. Okay.
But that doesn't happen. In imbal, like if you want to couple it with a well deliverability model, then you have to have it in Prosper. And in Prosper, you don't have this option. You can have a skin, a constant skin, mechanical skin, or something like this, which is accounted for the logic.
Okay, so an alternative is QG is KH over log RERW plus a blockage skin, and you use the integral P over, I know it has gas pseudopressure integral for dry gas. Okay, that would be an alternative, which is not probably a good alternative, but because the blockage skin changes over time because of the well stream becoming leaner because you have different degrees of undersaturation. A lot of things that come into what this effective blockage skin is so, but this is an alternative, less accurate. Say so. But even if you use this thing here, the problem in doing that is to know it's very sensitive to knowing the right producing CGR. And if you're off this 5%, then you have way too much blockage effect being calculated. Because if you use this assumption here for the flow equation, that's what Odell and Miller did, and you get only region 1 throughout the entire two-phase region. You don't have a region 2. So then you're going to be over-predicting, and possibly a lot, the blockage effect. That's the problem here. So, and there's really no good way to know whether it's a 2% or 8% and how it changes over time. There's nobody come up with the solution for that. How to treat region 2, the incoming flowing CGR to region 2 and the outgoing flowing CGR to region 2. Nobody's figured that out with enough accuracy to get this, to be able to use this model. Now, I think probably the one getting closest to that is this paper by Bob Mott. But it's approximate. And it's probably not in imbal. So anyway, I just want to make it clear that, yeah, the material balance can be done reasonably well if you have CVD data. But the rate equation is not going to be right.
Yeah, but like this uncertainty in the RP value 2 to 8%, it is going to affect the region 1, right? Region 1 performance.
Well, the problem is that you region 1 goes everywhere, all the way out to the initial dew point if it's undersaturated, or all the way out to the average reservoir pressure if it's saturated. So the point is region 2 disappears. And this slice of region 2 where KRG is 0.92, if that's over a 1,000-pound pressure interval, that's a big chunk of area that you lose most of by introducing the steady state assumption. KRG is not 0.92, it's 0.29, or you lose a lot of that area.
But how do you lose that?
Sorry, excuse me, Curtis. In one of my previous projects, I use I added the extra pressure drop in VLPs. Is it right approach? Like the pressure drop due to condensate skin into the VLPs.
Yeah, if you can build a pseudo VLP, vertical lift performance curve, that incorporates the condensate blockage skin, the 3, that's certainly a good way to do it. I've never.
You did it the first time.
Yeah, we did it to confirm, but I've never heard of it being used. Yeah, I mean that would definitely be the best solution. Now that's. So you've actually done that in imbal or just in Excel or how?
No, so we have IPSM model, like the gap model for shear water cluster. So for that, I use the extra VLPs, and then using just an Excel to add it's like a fudge factor into the pressure drops, added another section, you have 3 types of pressure drops, and then add the condensate drop skin over time.
It's basically the GP as a pseudo VLP tubing table.
Exactly.
Yeah, that's absolutely it's a very good idea. So tubing table. Yeah. No, that's Yeah, can definitely be done, and it's as accurate as the implementation like Eclipse 100. So yeah, that's definitely a good way to do it. Absolutely. You can also do that in a simulator that doesn't have the GPP option, but the problem becomes if you have a real tubing table and they don't allow kind of a chained in series series of several tubing tables, then you have to start. Then you have it becomes more complex. You've got to have the actual true tubing pressure drop plus the pseudo pressure drop, and you can probably get some pretty complicated a single composite tubing table that has both true tubing pressure drop plus the condensate blockage region pressure drop. That's I don't think I've seen that done by anybody, but it probably can be done, but I haven't seen it done by anybody. Okay, thank you for that comment.
So for gas condensate, is it okay if we ignore the condensate and dry gas BG to do material balance calculation, ignoring the condensate completely?
No, that's this point up here that basically you need to use the two-phase Z factor. It's that simple. Instead of the physical gas Z factor. So this you need.
Okay.
Yeah. So you need the two-phase Z factor, and you need the wet gas concept to use it to do the material balance correctly. Okay. But did anybody else use MBAL for gas condensate and can verify whether this is actually being used in MBAL? That you read in the solution oil gas ratio as a function of pressure, and that it applies this approximate assumption here. You've done that, Bilal. Has anybody else done that? So do you input only the little RS curve, or what about the BGD?
You can enter the full Blackwell table.
The entire Blackwell table you can enter. Okay.
Or you can enter an equation of state also.
Okay. All right. So then that's okay. So that was point 4, and I was going to try to find this link to Bob's paper. Maybe this one here. Not sure. Let me see. I get several. I think it's one of the latter papers. calculating the OGR. Okay, so this is this new method. The new method for calculating. Yeah. Yeah. So this, if you wanted to try to use this, this is the paper 86298, where I think he tries to treat this region 2 approximately. So that's 86298. But again, I think it's approximate. It's not. It's definitely better than using producing equal to the solution, for sure. So. Okay, and then the last point on this this thing here was the pseudopressure integral can be extended to include high velocity and IFT effects on relative permeability. Improvement for high capillary numbers and reduction from inertial non-Darcy flow. We're going to talk about that in some detail here after lunch. So we'll come back to that. Okay. This we've seen before. And this this we haven't seen in the sense we've seen the oil saturation from a model. This is actually the oil phase mobility corresponding to the oil saturation. You can see how that basically drops to 0 and more or less defines the region 1, region 2 boundary. And then what's interesting about that's shown here, and that's also, I think, shown in this paper by Bob Mott, is how to calculate from model results the flowing composition or the flowing oil-gas ratio from the model. Okay, so you can do that, and then you can actually see that the flowing oil-gas ratio. It's not something the model gives you. You have to calculate it from saturation, mobilities, and so forth. What that flowing OGR is. So, and you can see there's a big difference between what's at the wellbore, what's being carried in solution is only 8 barrels per million here. What comes into region 1 from region 2 is 26 barrels per million. And what remains flowing throughout is 26 barrels per million, of which only 8 out of it is being carried in solution at the wellbore. So you all see this? The green triangles is showing as you go from the as you go from leaving region 2, entering region 1, looking at the pressures, the amount of barrels in solution in the gas flowing is shown in the green here. Starts at 26, ends up at only 8. But the flowing well stream maintains this 26 throughout region 1.
Okay.
So what you can say is at the wellbore, 26 minus 8, 18 barrels, is actually flowing as a mobile oil phase at the wellbore. And it was being carried in from region 2, all in solution. Any questions about that or?
Just a comment. This oil is coming out of gas phase. It's mainly because of the pressure drop, right?
It's retrograde condensation.
Yeah.
Exactly. Yeah, it's the little RS curve. It's how many stock tank barrels can be held in solution in the gas phase, and as you lower the pressure, it's fewer and fewer barrels. So it goes from 26 barrels can be kept in solution, down to 8 barrels can be kept in solution. And these 18 barrels here that are flowing in as a they're flowing in with this mobility. This oil mobility is what's required to get all 26 barrels flowing into the wellbore. So you see here you don't need much oil mobility. You can see that in the oil mobility up here being much lower.
And if I try to bring a little bit more complication, the dissolved water that will also would drop as we enter into the retrograde condensation region.
You're talking about the water solubility?
Yeah.
Okay, so
The dissolved water.
yeah, so water solubility in the hydrocarbon phase, the way the water solubility works, you can kind of just say that you've got a hydrocarbon phase and not a gas oil, because the water molecules will partition both into the gas and the oil, okay, in a little bit different amounts, but not radically different amounts. So if you look at water, solubility in the hydrocarbon phase, phases, then in general, we call that little RSW, okay? And that's talked about in detail in chapter 9 of the book. So this is going to have a monotonic relation with pressure that's looking like this. Okay. So what happens is that, out here if you're out here in the reservoir here, the gas flowing in from far out in the reservoir, it's in equilibrium with water, the connate water. So this is the RSW of that initial gas flowing in from afar. Okay. And as it flows towards the well, that gas is able to pick up water, okay, because it can have a higher and higher solubility. It will, it'll see new water and it will dissolve that water, okay? So basically the hydrocarbon flowing phase, be it a gas or a gas plus oil, will take with it water molecules all the way to the wellbore. It'll keep stripping water molecules. It'll keep stripping water molecules in increasing amounts. So if you have a very low bottom hole flowing pressure, then of course you're picking up a lot of water near the wellbore. And in fact, what will happen typically for dry gas wells or any kind of well is that the water saturation near the wellbore will disappear. And often you'll get salt that was in the water originally will precipitate as kind of a scale.
Yeah, that's what we study during our scaling studies.
Right. So that's going to happen, and you can get that. You typically get that in the formation, but it doesn't often become a problem. And if it does, then you can usually drop water down into the wellbore, wash it around near the wellbore, and it'll dissolve that salt, and you can bring it back up. You can also get water precipitating in the well bore, which is even more common. But typically to get that, you need a little bit of free saline brine flowing into the well bore. That's usually when you start seeing the scale and salt in the well bore itself. You usually need not very much, a barrel a day of brine flowing into the well bore. It mixes with all of the gas in the well bore, and then you start getting this precipitation in the well bore. But yeah, the water saturation near the well will basically be disappearing some distance out. But the solubility curve here is more or less independent of whether it's a single phase gas or a gas oil mixture. Okay. So just to, so if you look at radius and water saturation, then if your initial water saturation is something like that, then you would expect that over time, 1 week, 1 month, 1 year. I don't. There's some people that I think UT and there are some publications on this, but basically you can kind of see this water disappearing over time. I think in the JIP with condensate blockage, we actually did experiments with the, basically vaporizing the water out. So we ran with cores without any condensate water at all and compared it with the same kind of rel perm that we got with water and without water. So. Without it having much effect, in fact. Is this address the issues?
Yes, thank you very much.
Okay.